I'm going to start this video by acknowledging that I was moving pretty fast through the last one, which I don't really need to acknowledge because everybody kind of knew that. And so I wanted to just track back to this slide and talk about a question that came up in class about what do we mean by shells and what do we mean by subshells. And it's listed here, but I just went through it so quickly in the previous video, I wanted to slow down and say it again. Orbitals at the same with the same value of n form a shell. So this would be the n equals 1 shell. And the n equals 1 shell contains one orbital. So you can only have an s at the 1 level because you can only have an L equals 0. You can only have one s orbital at any level. So at the 1 level, you only have one orbital. And so we would say that in the 1 shell, n equals 1 shell, we have one orbital. Now in the n equals 2 shell, and again, everything with the same value of n is a shell, we have 4 orbitals because we can have an s orbital, and we can have 3 p orbitals. Those s's and p's are referred to as subshells. And so this would be the 2s subshell. An s subshell can only ever have one orbital because when there's only one possible value of m sub l when L is equal to 0. A p subshell will always have 3 orbitals. And so in this case, the 2 shell, the n equals 2 shell, has 1 orbital in the 2s subshell, 3 orbitals in the 2p subshell for a total of 4. We could go on, but that's the terminology that was perhaps lacking from the last video. Well, let's move along and actually talk about the shapes of these orbitals. It's not super important that you know this right now, but when we get to orbital hybridization in chapter 9, it becomes useful to recall what the shapes and orientations of orbitals are. And so as you'll recall, when L is equal to 0, that's called an S subshell. And so all S orbitals are spherical in shape. The actual distribution, probability distribution from the Schrödinger equation would look like this, but we would depict it as a sphere. So the 1s orbital is the smallest, it's closest to the nucleus. As they get large, as they go up in energy, they get larger. So a 2s orbital is larger than a 1s orbital. A 3s orbital is larger than a 2s orbital. Again, they are just depictions of this probability density. But anytime you have an L equals 0, that's an s orbital, there can only be one, and it is spherical. You'll recall that when L is equal to 1, that's called a p orbital, and there are 3 p orbitals possible. They have this electron density of 2 lobes, which we tend to depict in this way. It's often referred to as a dumbbell-shaped orbital. And as you'll recall, because when L is equal to 1, there are 3 possible values of m sub L, there are always 3 p orbitals in a given p subshell. And they lie along orthogonal axes. So we would refer to px, py, and pz. D orbitals are more complex, and we're not really going to worry ourselves about exactly what planes and axes they lie along, but there are 5 of them. 4 of them look like just crossed X's. And then the 5th one, for reasons that I don't even understand because I'm not much of a computational physicist kind of guy, looks like a p orbital with a donut around it. Those are the d orbitals. And then f orbitals, I'm not even going to show you. It's hard to get depictions of f orbitals, even find them online, but you could if you wanted to. Let's talk instead about the energies of these orbitals. In a 1 electron hydrogen atom, all orbitals at the same principal energy level have the same energy. Okay, so obviously at n equals 1, there's only 1 orbital, so we don't really need to apply that here. and a box here represents an orbital. The question is, now when we get to the 2 level, we've got a 2s orbital. We've also got 3 2p orbitals. In the hydrogen atom, they all have the same energy. And so the y-axis here is energy. And you can see that for the hydrogen atom, all of the 2-level orbitals, whether they are s or p, have the same energy. And at the n equals 3 level, all 9 orbitals, whether they are s or p or d, all have the same energy. When a set of orbitals has the same energy, all of the orbitals in that set have the same energy, we refer to that as degenerate. And so a subshell of orbitals will always be degenerate. 3d orbitals will always have the same energy as each other. 2p orbitals will always have the same energy as each other. But in the hydrogen atom, they are also degenerate between subshells. So everything at the n equals 2 level has the same energy. Everything at the n equals 3 level has the same energy. They are all degenerate. That changes when you put more than one electron into an atom. What that has the effect of doing is taking these subshells that are degenerate in the hydrogen atom and splitting them apart in energy. And the s orbital goes to a lower energy, and the p orbital goes to a higher energy. And so you can see that once we put more than one electron into the atom, it splits the energy of the 2s and the 2p. The 2s goes lower, the 2p goes higher. It splits the energy of the 3 level. The 3s is lower than the 3p. The 3p is lower than the 3d. It splits the energy of the 4 level. The 4s is lower than the 4p, etc. So as the number of electrons increases, there is repulsion between electrons, and that has the effect of splitting the subshells. You'll notice again, as I mentioned before, within a subshell, the orbitals are always degenerate. 2p orbitals will always be degenerate. 3p orbitals will always be degenerate with each other. But the 2p orbitals are now no longer degenerate with the 2s orbital. And this, by the way, is kind of gives you some explanation of why the line spectrum of hydrogen is so clean. Because it doesn't matter if I'm promoting from the 1s, which is the ground state, up into the 3 or 4 or 5 level. It doesn't matter which orbitals it goes to at the 2 or 3 or 4. They're all degenerate with each other. So there aren't that many energy transitions in a hydrogen atom. By comparison, when you start looking at these splitting within the 2 level and the 3 level and the 4 level at multi-electron atoms, you can get to understand why just even the spectrum of helium, which only has one more electron than hydrogen, is much, much more complex line spectrum than the hydrogen spectrum. And that's because you get this splitting. Well, let's talk about the question of, all right, we've talked about these orbitals. We've identified them by name, 2p, 3p. We can associate that with a set of quantum numbers. The question is, how many electrons can occupy a given orbital? Well, to answer that, we have to state what's called the Pauli exclusion principle. And the Pauli exclusion principle is that no 2 electrons in the same atom can have exactly the same energy. And so what that means practically is that no 2 electrons in the same atom can have the same set of quantum numbers. And so in other words, if I've got an electron with a particular set of quantum numbers and I put another electron into that atom, that electron must have a different set of 4 quantum numbers. I'm sorry, of quantum numbers. I haven't actually gotten to the fact that there's a 4th one yet. I gave the game away there. And so that might seem to imply that only one electron can go into each orbital, right? Because each orbital is described by a unique set of 3 quantum numbers. And so if no 2 electrons in the same atom can have the same set of quantum numbers, it would seem as though you could only put one electron into each orbital. Well, that turns out not to be true because of the 4th quantum number, which I just sort of let the cat out of the bag a second ago, which is what's known as the spin quantum number. And it is designated as m sub s. So m sub L is the magnetic quantum number, m sub s is the spin. There is a fourth quantum number, the spin quantum number, m sub s, and that describes the rotation of an electron on its own axis. And the spin quantum number has two allowed values, plus 1/2 and minus 1/2. And so if it's spinning in one direction, it's got a plus, and if it's spinning in the other, it's got a minus. You don't need to worry about associating a particular number with a particular direction of spin. Just know that an electron can spin in two directions, and therefore it can have two spin quantum numbers. And so therefore, that makes the answer to the question, how many electrons can occupy a given orbital? 2. So if we take a look at the simplest, lowest energy orbital that exists, that is our 1s orbital, that 1s orbital is described by these three quantum numbers. N is equal to 1, L is equal to 0, m sub L is equal to 0. If I've got these three quantum numbers, which are the only three allowed at the n equals 1 level, that is saying I am describing the 1s orbital. Well, if I put an electron in there, the first one in, I'm just going to arbitrarily say has the spin of plus 1/2. So this electron has 4 quantum numbers, 1, 0, 0, plus 1/2. But I can put another electron in there now that has these 4 quantum numbers, 1, 0, 0, minus 1/2. And therefore, because these two electrons do not have the same 4 quantum numbers, they have 3 in common, but not the 4th, they can both occupy the same orbital. So you can put a maximum of 2 electrons into any given orbital. By convention, we always draw the first one into the orbital with the arrow pointing up, the second one with the arrow pointing down, but these don't correspond to any specific quantum numbers. It's just a drawing convention. Okay, so now we can go back to our diagram of energies of orbitals and say, well, we can put 2 electrons into the 1s orbital. We can put 2 electrons into the 2s orbital. Therefore, we can have 2 electrons at the 2s subshell. We can put 2 electrons into each of the 3 2p orbitals, and therefore we can have 6 electrons at the 2p subshell. That follows for the 3s and the 3p, 2 and 6, the 4s and the 4p, 2 and 6. And when we start talking about d orbitals now, we can put, there are 5 orbitals, we can put 2 into each one, so a total of 10 electrons at the d level, in a given d level. Therefore, we can put at the 1s, at the n equals 1 level, we can put a total of 2 electrons into those orbitals, into that orbital. Oh, something has gone, oh, I'm pressing the wrong button. That's why everything's going wrong. At the n equals 2 level, we can put a total of 8 electrons into orbitals at the n equals 2 level. We can put a total of 18 electrons into orbitals at the n equals 3 level. So let's now talk about actually filling orbitals with electrons if we were talking about specific elements. And this is the most animated slide I have ever prepared for an AP Chemistry QOD. I believe it has 24 different separate animated steps. But what I'm going to do is take this diagram and draw it in a way that I like to draw it, which is to put everything essentially straight up on top of each other. And I'm only going to go through the 3p level. So I've drawn in ascending order of energy, the 1s, the 2s, the 3 2p's, the 3s, and the 3 3p's. And if we think about, well, let's consider an element like hydrogen or boron or sulfur or carbon, and how are we going to place the electrons for those elements into this orbital energy diagram? We're going to follow what's called the Aufbau principle. And Aufbau literally is just a German word that means filling up. So I'm going to place electrons in the lowest energy available orbital that's available. So if I have a hydrogen atom in its ground state, it has 1 electron, and that is going to be in the 1s orbital. If I have a helium atom, which has 2 electrons, then I'm going to put that second electron into the lowest available orbital, the lowest energy orbital available, which is still the 1s orbital. And so therefore, a helium atom, its electron distribution would look like that. If I go to a lithium atom, which has 3 electrons, it looks like this. A beryllium atom, which has 4 electrons, its distribution of electrons would look like that. If I get to boron, I'm putting it here. Now I've got the question of, I go from boron to carbon, I've got a 6th electron. This level is degenerate. Does it matter whether I put that electron into this orbital or into another orbital? And it doesn't matter whether I put it up or down. And so now we're going to appeal to a thing called Hund's rule. Hund's rule says that when you're placing electrons into degenerate orbitals, you're first going to put single unpaired electrons into each orbital and give them the same spin, and then pair them up. So the electron distribution in a carbon atom would look like this. I'm going to put it in a separate orbital with the same spin. Then nitrogen. Now when I get to oxygen, I start pairing up. Oxygen, fluorine, neon. Therefore, the electron distribution in a neon atom would look like this. Now I'm going to keep going. Oops, wrong arrow again. Sodium has 11 electrons. Its electron distribution would look like that. Magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Well, you may have noticed something here that corresponds to the periodic table, which is that you can place a total of, you can accommodate a total of 2 elements at the 1 level, and there are 2 elements in the first row of the periodic table. You can accommodate 8 elements in the 2 level, and there are 8 elements in the second row of the periodic table. And you can accommodate 8 elements at the 3 level through the p orbitals, and there are 8 elements in the third row of the periodic table. Well, that's as far as I'm going to go. Tomorrow we'll talk about what's called electron configuration notation and the various blocks of the periodic table. This is shorter than 20 minutes. I hope you're happy. And I will talk to you soon. Bye-bye.